In this video, we will prove a theorem which is very useful to check the convergency of sequence of functions, either it is uniformly convergent or not. So theorem is, if f and x is a sequence of continuous function. So this is very important here. Sequence of continuous function on a given interval, closed interval AB, and suppose f and x converges to fx uniformly, then f of x is also continuous function. This is continuous function. That means if sequence of continuous function converges uniformly to a given function, to a function, then the limit function must be continuous. So proof is, let us consider a uniformly convergent sequence of continuous function f and x which are defined on closed interval AB, and let small fx be the limit function of sequence of function f and x, such that f and x converges to fx uniformly. Now we will prove that this function fx is continuous on closed interval AB. So for this, let C belongs to closed interval AB be an arbitrary point. If fx is continuous at that point, and because C is arbitrary point, so we can say fx is continuous throughout the domain. So that's why we take an arbitrary point C between closed interval AB. Then for all x belongs to closed interval AB and for all natural number, we know that mod of fx minus fc is equal to mod of fx minus fnx plus fnx. So we can cancel out these two terms, and similarly we add and subtract fnc and fnc minus fc. So we add these two terms fnx and fnc, and same subtract from the, and also subtract from these equations. So after simplifying this, we get mod of fx minus fnx plus mod of fnx minus fnc plus mod of fnc minus f of c, because we know that mod of a plus b is always less than equal to mod of a plus mod of b. So this is our equation number first. So this is our equation number first. Because sequence f and x converges to fx uniformly, so by definition of uniform convergent sequence, for each epsilon greater than 0 there exists an integer, positive integer, or we can say a natural number, such that for all x belongs to closed interval AB, this inequality always true. That means mod of fnx minus fx is strictly less than some epsilon, here epsilon by 3, for all x belongs to closed interval AB, and for all natural number which are greater than some particular number capital N. Now taking x is equal to c in equation number second, we get, because this inequality hold for all x, so for particular c inequality second we also true. That means fx fc, put c here, and fnc is also less than epsilon by 3. This is equation number 3. And because sequence of function f and x is continuous throughout the domain closed interval AB, So that's why f and x is also continuous at a point x is equal to c. And by definition of continuity, for each given epsilon there exists a delta greater than 0, such that whenever x belongs to c minus delta, c plus delta, mod of f and x minus f and c will be less than equal to epsilon by 3. So this is our equation number 4. So from equation 1st, 2nd, 3rd and 4th, we have 1st, 2nd, 3rd and 4th, we have mod of fx minus fc is less than epsilon by 3 plus epsilon by 3 plus epsilon by 3, that is less than epsilon. And that means fx is continuous at point c. But because c is arbitrary point of closed interval AB, so fx is continuous throughout closed interval AB. So if sequence of function converges uniformly to a function fx, then fx must be continuous. That means the assumption of continuity of the limit function is only necessary condition for uniform convergence of sequence of function, but not a sufficient condition. That means it may be happen that sequence of function, the limit of function fx is continuous, but still the f and x is not uniformly convergent. So second important thing is here that from the above theorem it follows that if limit function fx is discontinuous on closed interval AB, if limit function of sequence of functions is discontinuous on closed interval AB, then sequence of continuous function cannot be uniformly continuous. So this point is very important here. And in view of these 2 points, we can check the convergency of sequence of functions. For example, prove that the sequence of function where the sequence f and x is defined as tan inverse nx is not uniformly convergent on closed interval AB. So f and x is equal to tan inverse nx for all x belongs to 0 to 1. If we put x equal to 0 here, we get tan inverse 0, and we know that the tan inverse 0 is always 0. That means f and 0 is equal to 0, that is constant function, and we know that constant function is always continuous. Similarly, if we put x is equal to 1 here, we get tan inverse n. So this is tan inverse nx. So we get tan inverse n, and when moving n from 1 to infinity, we get a continuous function. So for all values between 0 to 1, we can see that tan inverse nx is a continuous function, but its limit function, that is fx, which is obtained by taking limit n tends to infinity, is not continuous because its limit function is equal to pi by 2 when x lies between 0 and 1, and its value is 0 when x is equal to 0. Because if x is not equal to 0 and less than 1, then when n goes to infinity, tan inverse x goes to pi by 2. So when x is not equal to 0, the limit is pi by 2, or when x is equal to 0, its limit is 0. So fx is pi by 2 when x is greater than less than equal to 1, and at x is equal to 0 it is 0.